Okay, getting the energy equations for simple harmonic motion. First thing is we've now got our horizontal oscillating mass here, where this spring is such that that's the rest point and the mass goes between here, and the force is always towards the equilibrium point. So this would oscillate something like that, backwards and forwards with time going down here. When you plot the force for this, you'll find that the force is at a maximum at the amplitudes, and because if you've got positive amplitude you've got negative force, it's over here, and if you've got negative amplitude you've got positive force. The force is pushing it towards that way. So you end up with a straight line graph through the origin where the force is negative a constant times the displacement. So it's got a negative gradient, and that spring constant K is in that equation there. So if we've got the equation F equals minus Ky, and force is mass times acceleration, so mass times acceleration is minus K times y, the acceleration is minus K over m times the displacement, which is good news because that is actually our defining equation of simple harmonic motion, that acceleration is a constant times y, or a equals minus omega squared y. In this case, the omega squared is equal to k over m. So you can have an equation for the force of something in simple harmonic motion is F equals minus m omega squared y. We're going to come back to that equation later on, so I'll keep that bit of paper handy. So what we're after is the energy that the mass has at any particular point out here, y, due to the spring potential energy. We could try and work that out by the work done, EW equals force times distance, but that doesn't work because the force actually depends on the y displacement. Because F is equal to minus Ky, those two are variables, so you can't just multiply them and use work done that way. You can, however, use calculus, where the work done is the integral between y equals y and y equals 0 of the force with respect to displacement, and that will give you what you're after. So we need an equation for force in terms of displacement, which is where this one comes in again. So we've got F equals minus m omega squared y. If I put that in over here, we've got EW equals integral between y and 0 of m omega squared y dy. I'm going to take out the constant either at the front of the integral, so we've got omega squared integral of y and 0 y dy. The integral of y is half y squared, so we end up with the work done against the spring potential energy is half m omega squared y squared, and that will work for any value of y, and that is the formula for potential energy for a spring system. This actually works quite well because it's actually the area under the force displacement graph, and that area under a graph should be familiar from doing distance from a speed time graph or energy stored by a capacitor under a QV graph. It's the same principle of integrating force with respect to displacement. So that's the potential energy and the spring constant.